Okay, we'll talk about generalization of deep neural networks. We've learned a lot about classical learning theory, learn about generalization error, learn a lot about, hypothesis class complexity, infinite hypothesis class complexity, and so on. We also learned about boosting, adder boost, which is a very interesting way of understanding how ensemble methods dealt with smartly would actually give you a very powerful, strong classifier with very desirable empirical performance as well as generalization error performance. So today, we will talk about generalization of deep neural networks. I will start with a paper. That a lot of you have read it. It's a very popular paper. If you haven't, well, I wanted to emphasize again, please read the papers before class. I think if you didn't read the paper coming to the class, it will be rather difficult for you to digest the lecture. So also, we will not do like a lecture style kind of session today. We will be more focused on discussion, right? I'll ask a lot of questions and I hope to get answers from you guys. Of course, you can also feel free to ask questions anytime. But the first paper I'll talk about is this very famous paper. It's an empirical paper, but it kind of inspired a lot of discussion about understanding the generalization of deep neural networks. And this is essentially called Understanding Deep Learning Requires Rethinking Generalization. It is now it is 2020, so it's rather old, I would say. Well, it's not that old, but it's a couple of years ago. Deep machine learning has developed, so fast recently. It's developing so fast. So there are a lot of follow-up papers coming out from this paper, but I still think this paper is worth reading as the first paper introducing us to understanding the generalization of deep neural networks. Well, so I put the archive link here, but also send the link. I send the TAs also asked you to read the paper before this lecture. So there's this mystery. Of course, this is in 2017. So there's this mystery, despite the massive size, the deep neural or these kind of exhibited small difference between training and test performance. So people have seen a lot of, smaller gap between test accuracy and the training accuracy. So generalization gap is small. So why is that, right? So conventional wisdom says, kind of you have this generalization error because either, it's some property of this model family. So it means that the model family has a small complexity, or the regularization techniques used during training would help you have a smaller generalization error. This is again resorting to this first idea of the property of the model family, because effectively these regularization techniques can be thought of as like effectively restricting the model family. So now going back to our theory, is basically saying the complexity of a hypothesis class H is small. Okay. Right. So this is the convention wisdom, but this paper actually said, no, that's not true. It seems like traditional approaches fail to explain why a large neural network generalize well in practice, because numerically we can show that deep neural networks easily fit a random labeling of the training data. And if you recall the Rademacher complexity or the empirical Rademacher complexity, essentially the complexity of a hypothesis is essentially how well it can fit random noises, right? We've talked about this when we talk about empirical Rademacher complexity. And they're saying, look, experimentally, we've shown you that DNNs can just fit a random label of the training data very well. What does that mean? It means that very likely the empirical random complexity of these deep neural networks are just large, right? It could be one or something. So that's this, so-called traditional approach failed to explain why natural neurones generalize. But another contribution of this work is to bring it to people that generalization doesn't really help. Regularization doesn't really help. So this is different from what we thought back in 2016 or 2017, right? We think, you have all this kind of explicit regularization, implicit regularization, and we're hoping that these kind of regularization techniques can effectively restrict the model parameter, the model family, and therefore reduce the complexity of the hypothesis class. But is that true, right? So this paper, although there's no theory support, but it numerically showed that, so 3 experiments show that the DNN's ability to fit random label is qualitatively unaffected by explicit regularization. So this is kind of concerning, right? If you believe that regularization would reduce the model complexity, this paper showed you no, it doesn't affect the model complexity at all. And the model complexity can still be very large. So that's basically my take on, a very high level summary of this paper. So now I wanted to ask if people have any questions regarding the high level understanding of this paper. I'm also gonna clear all your thumbs up and thumbs down, okay. Oh, so I hope we can use some breakout rooms today, but Aviva, did you tell me that you have some technical problems with breakout rooms? Or do people have technical problems with breakout rooms? Okay. Okay. Okay, we'll try, okay? So Aviva, if you do have a problem, so yeah, we can try to see, okay? All right, so if there's no questions, I'm gonna proceed to more detailed understanding of this paper. So basically the general idea is clear and it's a very simple paper. I guess the simplicity is really helpful here because very simple ideas are, kind of verified through simple numerical experiments. And these numerical experiments are kind of convincing. Also kind of, showing us how our previous understanding of generalization in deep neural networks could be wrong. So before we go into the details, of course, we wanted to understand what they mean by randomization tasks in this paper. Okay, so what they did is they have a bunch of different settings. They have a true labels. So this is just the original data set without modification. You have a training data set. Again, so the training data set with the clean labels, no modification at all. So that's your true label setting. And they also have a partially corrupted labels. So what this means is that they were just independently with some probability, the label of each image is corrupted as a uniform random class. Okay, so just selecting some percentage of the examples and then with a uniform random corrupted as a uniform random class. So if there is just 10 classes, then you just with a uniform probability selecting from these 10 classes, and that's how you corrupt those p percentage of the examples in the training set. Okay, so that's called a partially corrupted label, and the corruption is just uniform random. Now the random labels, so is that all the labels are replaced with random ones. Okay, so this is a little bit different from partially corrupted label. And I believe this random ones is also kind of uniform random class. Okay, so also they have the shuffle pixel. What it means is that this random permutation of the pixels is chosen, then the same permutation is applied to all the images in both training and test set. Okay, so the important thing is that the permutation is the same between the training and the test. And yet another way, another setting they are using is this random pixel. So it's a different random permutations applied to each image independently. You don't have the similarities between the training and test. Okay. And lastly, you have this Gaussian randomization test. So a Gaussian distribution with matching mean and variance to the original data set. So, you have the original data set, which is some distribution that you don't know, right? You were just using a Gaussian distribution to fit it. And then, this Gaussian distribution is matching its mean and variance, and you use that to generate random pixels for each image. And apparently in this scenario, you're using the original labels here. So any questions?
What is meant by permutation of pixels? Like if the image shuffled, like the pixels.
Okay, I'm gonna ask, so this is a great question. I don't want you to answer, but I'm gonna ask people, other students to answer. Just, you don't have to get permission to speak up. Just unmute yourself and speak up.
So I guess it's like, say if you have numbers from 1 to 10 and it's in the increasing order, you just create one permutation of this. So for example, it could be in decreasing order, and then this is kind of a function which you would apply to your pixels.
Yeah. Well, so that's a good explanation, but I'm gonna ask people, have people heard about permutation matrix? So if you have a permutation matrix, you multiply this permutation matrix with a vector. So what happens with that vector? Maybe someone's familiar with this, can explain from this angle.
Oh, does the vector, I'm just guessing, the vectors like contents are the same, but they just get repositioned somehow?
Yeah, so that's a question. So someone can you confirm, or can you say no, that's not true?
Yeah, I'm pretty sure that's what happens, yeah.
Feel free to just unmute yourself. Don't worry. I think it will work.
Yeah, so I would say if on the first row of your permutation matrix, your fourth element is a 1, it means that you will place whatever element you had in the fourth position as your new first element, and so on.
Yeah, exactly. So basically, you're just permuting, the positions. So you can think about shuffling your deck of cards or something. You're not changing the cards, but you're just shuffling it. Does that make sense?
Yes, thank you.
No problem. Okay, so with these randomization tests, we're ready to understand this red marker complexity VC dimension. Since we've already only got out of this, we just submitted our homeworks on this. So this red marker complexity is commonly used in the flexible complexity measure of a hypothesis class and the empirical red marker complexity of a hypothesis class on a data set. This is x1 through xn. And such examples here is defined as this thing, right? So this is, we're very familiar with definition, and these sigma 1 through sigma n is just IID uniform random variables with half probability choosing +1 or other half probability choosing -1. So why do we do randomization tests, right? So this basically is kind of trying to mimic the kind of Rademacher complexity, right? So this Rademacher complexity definition really closely resembles the randomization test if you think about it, right? You're just trying to see how you can fit the random noise. As we've already discussed in class when we're introducing the Rademacher complexity, we're saying it is kind of like showing how each, in my hypothesis class, how these hypotheses can be used to fit any random noise from any direction in expectation, right? So here, I'm gonna ask, what is a hypothesis class? Like, what is H? What is capital H?
To set up all the hypotheses for a given concept.
True, but in the context of deep neural networks, what is H here?
Like all the possible settings of weights that we could have after training the model.
Cool. So very important that you've said the model, right? So that means you're referring to a specific architecture. You're not referring to all possible architecture in the neural network space, right? So, ResNet 34 and the ResNet 52 and so on, right? So you're referring to a specific, you call it model, but really it is equivalently just a architecture of a neural network you use here. And now you're saying all possible weights realization of that neural network. So that means, any weight you assign to this architecture, to the weights of the neural network is a hypothesis in that hypothesis class, okay? So that's what, during training, what are you doing? You're basically searching over all possible, you're searching over the F prime, or I would say H star in H, right? During training, you're not changing, unless you're doing some kind of adaptive, searching of the optimal neural network architecture. If you fix an architecture during training, what you're doing is essentially trying to find an H star within H that minimizes your empirical error, right? So that's exactly what we do, when we think about this estimation error or approximation error when we're thinking about generalization error. So that's the first, Radmar complexity measure, a definition closely resembles the randomization test. And Radmar complexity measures ability of H to fit random binary label assignments. And this is, we all understand it during our previous lectures. So the experiments actually render that Radmar complexity equals to 1 is a trivial upper bound that does not lead to use for generalization bound in realistic settings. So that's what they will be, this is what they claim, and we'll see in a minute. So, do you understand this big picture of this paper now? Okay, so now this is the first result. So in this figure 1 here, I'm just taking a screenshot of the figure. So they have the randomization test results, and you can see, this is fitting random labels and random pixel on CFAR10. Of course, you can see the first figure, A, learning curves. You're showing the learning curves under all these kind of randomization tests, right? True label, random label, shuffle pixels, random pixels, and Gaussian, right? So this A, what does it show? It shows that the training loss of various experimental settings decaying with the training steps. But kind of interestingly, what you see is, for instance, the true label really decays really fast, right? So you can see of course, we cannot really see any theoretical, our claims out of this one figure on one data set, but we kind of get like a rough understanding, or, maybe we believe this sample is, this kind of one experiment is, if it's representative of what we would observe in general when we do a deep learning experiment, then from this specific experiment, we're saying, it seems like, we can very quickly learn a true label data set, right? But this random label is pretty hard to learn. It takes us a while to converge to a small average loss, but what's surprising is it converges anyway, right? It goes to 0 after 15,000 steps. Okay.
I don't know if this was said earlier, but is the black line for Gaussian here? Is this just adding like Gaussian noise to the pictures?
It is not. That's very interesting. So I guess, I understand why you're asking this. This might be very related to randomized smoothing, but it's not a smoothing. What it is a Gaussian fit. So what it is just, you have a Gaussian distribution which matches the mean and the variance to the original data set. Does that make sense?
Oh yeah, I missed that earlier.
Yeah. Okay, any questions regarding these figure, the first figure?
I think something that is very interesting is that it seems that learning the actual features is easier than memorizing the data set, at least when you don't have much structure in the data set.
Mm-hmm. But the thing is, right, these random noises are very random. So it seems like, actually learning random noise is the most difficult, right?
Yep.
Like, you were trying to create really like I would say a covering of the space. But this is of course not rigorous. It's just, my way of interpreting what I would think about this.
Mm-hmm.
Yeah, very good point. So now, figure B is the convergence slowdown. What it showed is that the relative convergence time with different label corruption ratio. So you can see, so what is a label corruption? Remember, the partially label corruption is just the percentage of the labels that are corrupted with a uniform random label. So you can see as the label corruption increases, the time to overfit seems to be taking longer. Does that make sense? So why would we say this is time to overfit? Actually, I wanted to ask you guys a question. Once I've for example, for this random labels, once I've converged here, what does this mean? Am I fitting very well, or am I overfitting, or what?
Because it is
Oh, sorry, go ahead.
because it is completely random label, so it is taking time to fit to that data. I mean, it is difficult to fit to that data, but eventually it fits to that data.
Exactly. So, we know that because it's random, so we know that the test accuracy is going to be high. Do you agree with that? You cannot, you cannot have a very high test accuracy for random data. So that's for sure. Now, you're saying during training, so this average loss is the training loss. During training, I could get a 0 training error. So what does that mean? That means I will have a gap between my test error and my training error, because my test error is going to be high and my training error is 0. So what does that mean? The first thing you've learned when you the first few things you've learned when you learn machine learning. That's overfitting, right? There is a big gap between test accuracy and the training accuracy. That's overfitting. So what does that mean? This means that the time during training you've converge to 0, even for random data, is the time you need to overfit. Okay, so that's why they're saying this is the time to overfit. Does that make sense?
Oh, so the time to overfit is measured by testing each model on its training on random labels?
Yeah, it's the time need to training random data or doing this randomized, one of these random data. There are a lot of ways to do random data, right? So one of these random data, in this case, is just a corruption. So it's like the percentage of corruption. Even if you've, what I mean is like, if you have a percentage of corruption, so even if you're able to get a 0 training error, you're still overfitting because, you know, for the proportion of the corrupted data, you shouldn't have a 0 training accuracy. You're memorizing.
Yeah, makes sense.
Okay, so what they're saying is, you know, the relative convergence time was different label corruption ratio. You can see from this figure here. Now the third figure, C, is the generalization error grow. And you can see this is just the test error under different label corruptions. Okay, of course, they are also showing 3 different architecture of neural network, like inception network, AlexNet, and MLP here. Okay. Now, so I think very interesting thing here is that the stochastic gradient descent with unchanged hyperparameter setting can optimize the ways to fit to random labels or, you know, other randomization perfectly, even though the random labels completely destroy the relationship between the image and the labels. So it's basically just memorizing something that doesn't mean anything. It's just completely noise. Okay, so randomization test implications, right? So it basically implies that deep neural networks easily fit. I don't know if you agree with easily fit, but somehow using a relatively small number of steps, they are able to fit these random labels. So what does that mean, right? So the effective capacity of neural networks is sufficient for memorizing the entire data set. Okay, so these data sets are usually huge. You're saying, you know, I'm just randomly generating stuff, but nonetheless, this neural network is just able to remember the entire data set. Even optimization on random label remains easy. So they're saying, in fact, training time increases only by a small constant factor compared with training on the true label. Of course, you know, from the figure, you cannot really see, but I guess, you know, the authors have looked at the clock time and showed that it is just a small constant factor compared with the training on the true labels. And randomization labels is solely a data transformation, leaving all other properties of the learning problem unchanged, right? So you're using the same hypothesis class. You know, the learning algorithm is the same. You're still using, you know, I don't know, Atom, SGD, one of these things, right? So optimization is the same, learning algorithm is the same. Only difference is that you are just changing the data. All right, so you're just transforming the data essentially. Okay, so that's this part of, you know, randomization tasks. Is there any questions so far? Okay, so if no questions, we can move on to explicit regularization. You know, the second claim that the authors claim is that, you know, people believe that regularization would make the complexity of the family smaller. And is that true? So because there are 2 classes of regularization, explicit and implicit. So they first explore the explicit regularization. And, you know, these kind of regularization can often fall into 3 big categories. Of course, there might be other things, but I'm not sure if they covered everything. If you feel like there is another way of regularization, feel free to speak up. So the first one is the data augmentation, augment the training set while domain-specific transformations, right? So for image data set, commonly used transformations like random cropping or random perturbation of brightness, saturation, hue, and contrast, and so on, right? So these kind of random perturbations might be some kind of data augmentation for a regularization. And people do that a lot in these empirical experiments. Now, so the second way is the weight decay, right? So equivalent to L2 regularizer on the weight. You might have also, equivalent to like a hard constraint on the weights on the Euclidean norm, or you can have other kind of regularization, L1 regularization, L0 regularization, and so on, right? With the radius decided by the amount of the weight decay or something like that. So that's also a very commonly used way to do explicit regularization. So that's the second one. Actually, despite the discussion about generalization, the kind of weight decay or the kind of explicit regularization could be used in other scenarios. For example, understanding improving the robustness of the neural network and so on, right? So we can talk about this more later on. But today, in terms of the deep learning or generalization, one way of doing explicit regularization is the split decay. Okay. Then the third category is the dropout, right? I still remember when I was attending NIPS. Well, back then it's NIPS, now it's NeurIPS. Back then it's NIPS 2014. When I first heard about dropout, I was basically very skeptical about it. Back then I wasn't really working on deep learning. I was like the theory computer scientist that wanted to work on something that's more so-called principle or kind of, theory oriented and stuff like that, like, statistical models and things like that. So I wasn't really, keeping up with all deep learning literature, and somehow there's this huge buzzword about dropout. And even someone like me who wasn't working in deep learning started to look at what is a dropout. Dropout is very simple. It's simply, something really simple, but works really well. And that made a lot of impact, especially that year. So dropout is mask out each element of the layer output randomly with a given dropout probability, right? It's very simple. And people believe that this is a way of explicit regularization. And people seeing a lot of use cases of dropout and how successful dropout has been in a lot of different domains of, different applications of deep learning. So, so in this paper specifically, they're using that for ImageNet, Inception V3 ImageNet. But anyhow, this is more like a detail. So these are three different categories of explicit regularization. Now, they're showing some results. So now let's see. First of all, the explicit regularization may improve generalization performance, but it's neither necessary nor by itself sufficient for controlling generalization error. So you can see the table here, right? This table is the training and test accuracy of various models. So this is on CFAR10. I believe everyone knows CFAR10, right? If you don't know, it is that benchmark data set used in computer vision with 10 classes, shapes. It's relatively simple. Usually there is only one object in these data sets. I don't even remember what is the resolution or how many pixels are there in these data sets. Someone provide an answer.
It's like a 10 by 10 little square for CFAR10. They're very small images.
Oh, no, I don't think it's 10 by 10 though.
Okay,
they have 10 classes. If you think about the loss, the loss function, so your output labels is going to be in a 10, I think you're referring to the label space. Correct? Yeah, so it's 32 by 32. I believe so, if I remember correctly. But yeah, the labels is 10. So, you have these various models on CFAR10, and the performance with and without data augmentation and weight decay are compared, right? So you're comparing with the explicit regularization against, without explicit regularization. So you can see still, you don't see much difference, right? For example, you have inception, whether you have random crop or weight decay, or you have, I don't think yeah, there's no dropout here, as they said in the previous slide, that the dropout is only used in ImageNet. So they're only testing the random crop and weight decay. You can see with or without. For example, this ablation study is both with random crop, but one without, one with weight decay, one without. So you can see the test accuracy basically remain the same. Okay, and this is fitting a random label. Okay, so you can see, of course, it overfits.
So I have a question.
Yeah.
Just trying to think about, because this almost makes it seem as though regularization isn't really helping, but we know that in practice it can help us avoid overfitting.
Oh,
so
I don't think this message, yeah, that's a very good point. I don't think this message is saying regularization is not helping. Rather, well, you know, maybe people don't agree with me, but my understanding of this is that it's not saying that regularization is not helping, but rather it's saying explicit regularization is not enough to explain our confusion about the discrepancy between the theory and the practice.
okay.
What was the discrepancy, or what is, you know, the mismatch? The mismatch is that we're thinking that, you know, we have in practice we see the small generalization error, or, you know, the small generalization gap, but in theory we don't know how to explain it, because we thought that we are in a, you know, we thought in order to explain it we have to come up with a theory that the complexity is small. The complexity of a hypothesis class is small, but we can't. So that's the discrepancy here. So
thank
yeah,
you.
that's a very good point. I don't want you to misunderstand into, like, you know, explicit regularization is not useful. It's very useful. Implicit and explicit regularizations are very useful in a lot of scenarios, in a lot of other applications, maybe more than generalization, of course, right? So, you know, improving robustness and so on. But it is not the theory we should be using to understand the discrepancy between the theory and practice, or the gap between theory and practice.
Okay, that makes sense. Thank you.
That's very important. Thank you for this question. Okay, so that's, you know, the first message they're saying here. The second message appears that to be more of a tuning parameter. So they're saying this explicit regularization is more of a tuning parameter, often help improve the final test error of a model, but the absence of all regularization does not necessarily imply poor generalization. So it's saying, you know, with it is helpful, but if you don't have it, it is not the end of the world. You still have, you know, not necessarily the absence of these regularization would give you poor generalization error. Okay, so I guess, you know, which line of this table is showing that, right? For example, here, oh, shoot. So you can see my cursor, right? Can you? Yeah, this line, you don't have random crop, you don't have weight decay, you're getting 100 training accuracy, you're getting like, of course, this is for the clean data, right? So you still get a decent test accuracy, right? So that's why they're saying with this explicit regularization, yes, improves the final test accuracy, but without it, it's not the end of the world, right? Okay, so then the third message is, even with all the regularizers turned off, all the models still generalize very well. Okay, so you can see that with all of them turned off, generalize pretty well. Here, of course, this MLP, you know, doesn't have a very good generalization performance, even with implicit or even with explicit regularization. So, yeah, that's just something that's, you know, something different from today's topic. Okay, so any questions regarding this claim about explicit regularization? Okay. All right, so now, you know, after talking about explicit, they're talking about implicit regularization. So there is this early stopping. People have been showing that this is an implicit regularization using early stopping or batch normalization. And there is a lot of discussion about batch normalization over the past few years. And people have seen a lot of kind of controversial ideas about batch normalization. Even there was like some wrong implementation of batch normalization and so on. So there was lots of discussions there. But nonetheless, batch normalization can be thought of as an implicit regularization. It's a normalized layer responses within each mini batch, right? Okay, so in implicit regularization results in table 2 in this appendix, the authors show that, in the parentheses, the best test accuracy along the training process. So, in these parentheses, we're showing the best test accuracy. It confirms that early stopping could potentially improve the generalization performance. Right. Right. So, if you have some kind of early stopping, right? So, so the reason is that, for example, in this case, the 67.18 is, after how many epochs, the final result you get. But if you have like an early stopping, at some point, of course, you have to be stopping at the right point. But if you happen to be lucky, then you could get a potentially higher accuracy, right? 72.57. So that's what they mean by, in the parentheses, is the best test accuracy along the training process. So if you're early stopping, if you get lucky and you get, stop at the right time, so you could potentially get a better accuracy. Of course, I'm not an expert in understanding early stopping techniques, so I may not know, other techniques of how to do better early stopping. For those of you who may be working on this, might have a better idea than I do. Or if you wanted to comment on this, feel free to speak up. Okay, let's move on. So also showing figure 2 here, from figure 2a, it is showing the training and testing accuracy on ImageNet. Actually, I should say test here. Usually people don't say testing, right? It's training and test. Sorry about this typo. The shaded area indicate the accumulated best test accuracy as a reference of potential performance gain for early stopping. However, on CFAR10 data set, we do not observe any potential benefit of early stopping. Okay, so you can see you can see, on the right-hand side, the shaded area is just showing the accumulated best test accuracy as a reference of the potential accuracy gain for early stopping. You don't get better accuracy, or you don't observe any potential benefit of early stopping on CFAR10. So, sorry. Figure 2b is like compares the learning curve of the two variants of inception of CFAR10 with all the explicit regularizers turned off. And the normalization operator helps stabilize the learning dynamics, but the impact on this generalization performance is only 3 to 4%. So overall, nonetheless, what this slide is trying to say is that implicit regularization, of course, also help, but it's not the theory that we need to understand why there is a gap. So in summary, our observation on both explicit and implicit regularizers are consistently suggesting that regularizers, when properly tuned, could help to improve the generalization performance. However, it is unlikely that the regularizers are the fundamental reason for generalization, as the network continued to perform well after all the regularizers removed. And therefore, more importantly, what they're saying here is to understand the gap between theory and practice. we shouldn't resort to regularization here. So in conclusion, what this paper is saying is that the deep neural network models are in principle rich enough to memorize the training data. This situation poses a conceptual challenge to statistical learning theory, as traditional measures of model complexity struggle to explain the generalization ability of large artificial neural nets. Okay, so that's the first message here. And you know, this is indeed something really concerning, but in the next paper, we'll show you why this is actually a misunderstanding rather than a gap. Okay, so in this paper, the authors kind of claim it as a challenge or conceptual challenge to statistical learning theory. But is there really a gap? You know, actually the authors in the next paper we will talk about today show that this is not really a gap. It's just a misunderstanding or misinterpretation of the theory. Okay, so then the second bullet point of this conclusion is that we argue we have yet to discover a precise formal measure under which these enormous models are simple. And I actually agree with this. I think we're still not there yet. We haven't figured out a precise formal measure under which these enormous models are simple. So how do we measure this capacity of these models, right? So it's still a unknown or open question. So then lastly, another insight resulting from their experiments is that optimization continues to be empirically easy, even if resulting model does not generalize. So this is rather concerning, right? Common sense would be, you know, if I'm learning just random noise, my optimization should have a hard time converge, right? There's no really like structure in the data, right? It is just random noise. Common wisdom would think I should have a hard time converge. But, you know, unfortunately, empirically, we're showing even if the resulting model does not, even if the resulting model does not generalize, or you're memorizing, you know, a lot of random stuff, the optimization still to be relatively easy. This
I have a question.
Right.
What does simple mean? You have simple here.
Where do I say simple?
On the second bullet point, you say simple.
Oh, meaning the complexity is small. So, you know, we are just kind of using the randomization test to show the Rademacher complexity of these could be very high, right? As close to 1.
But why do you want it to be small?
Yeah, that's actually the misunderstanding of the theory. We'll talk about that in the next slide. We're saying
Okay.
that not necessarily we want, but here I still agree with this argument. You know, there should be some measure that kind of tells us that these enormous models are actually simple. That's why they could generalize, and we're not there yet. So I still agree with this argument, but we'll talk about this in the next paper about this misunderstanding of this gap. Okay. Yeah, in a few slides. So let's go back to the third bullet point. So this shows that the reason why optimization is empirically easy must be different from the true cause of generalization. Okay. So this is again just a way of trying to guide us through. If you wanted to understand the generalization, do not understand it from the, you know, the hardness of optimization point of view, right? So that might not be a good starting point to understand the generalization. Okay, so yeah, I want to say don't overinterpret these results. You know, so first of all, these results are empirical. So, you know, don't think that they are trying to criticize regularization or so, right? Also, people might be concerned that, you know, does this mean that statistical learning theory is not useful or is just wrong? actually we'll see in the next paper that statistical learning theory is still very useful. And actually in the fourth paper, we will read for generalization, understanding of generalization, we will see statistical learning theory is actually very useful for understanding the generalization ability of neural nets. So this paper seems to, say that there is a gap. We cannot trust statistical learning theory, but that's not true. Okay. So any questions before we move on to the next paper? Unfortunately, I think we only have, so how many? 23 minutes left. Is that right? We might not have time to cover all of second paper, but we'll try. Any questions? Okay, I hope everyone has, if you read the paper, you agree with what I say, or if you don't agree, speak up. If you haven't read the paper, hopefully this serves as a good introduction of the paper, and please read it after class. I really hope that we can read it before class. Okay, but if you have ICR deadlines or if other deadlines, please read it after class. Also, the good thing is we have the video recording, so you can always go back to the recording if you have something that you don't understand. Okay. All right, so the second paper I wanted to introduce is this generalization in deep learning. Also, I want to say this is an old paper, but very surprisingly, today I looked for the archive link of this paper. When I was doing that, I realized Kenji actually is actively updating the paper. I saw an update even in 2020, like this year, so which is very impressive. Okay, so let's see. So overall, this paper idea is rather interesting. First, with a direct analysis of neural networks, this paper presents a mathematically tight generalization theory. So this is rather impressive. To partially address, we'll see why it is partially addressed, an open question, open problem regarding the generalization of deep learning. Okay, so also, unlike previous bound-based methods theory, main theory is quantitatively as tight as possible for every data set individually. This is, again, a very, very interesting result, right? You can see all the statistical learning theory we learned usually are not like for every data set individually tight, right? So this is very impressive. This is saying main theory is quantitatively as tight as possible for every data set individually, while producing qualitative insight competitively, right? So of course. Now, also they claim that the results give an insight into why and how deep learning can generalize well, despite its large capacity, complexity, possible algorithmic instability, non-robustness, and sharp minima, answering to an open question in the literature. So I think, actually, since we don't have a lot of time, I wanted to maybe separate the presentation or discussion of this paper into today's lecture, like the first half of the paper. Then I will leave a few, maybe a few part of this paper to you to understand it individually. Oh, what's going on? Sorry. Okay, so ignore this, ignore what's in here, just look at the top. So this paper actually had a very good, I would say, a introduction, or like a kind of survey of how people address the generalization gap in deep neural networks. So everything started with this generalization gap, R of FAS, R of F sub AS, R of S, F sub AS. So what is this? A is the learning algorithm. Okay, so now in our PAC learning framework, It's just, we say there exists an algorithm, but here is a algorithm you use. So it denotes A. Okay, S also is just the sample. So it's the training data set, which is drawn from a underlying distribution. But here, no matter what, it is just a sample with M examples. Now R of F sub AS. So first of all, what's F? F is just so-called I would say the hypothesis. You would think about it as the output of your neural network. Okay, so of course the R of FAS is nothing but just the expected error. It's the same as what we learned in class. So R just denotes the true error, right? Of course, the Y is hidden here. The label is hidden here, but you can imagine this just means that some, either 0, 1 error between like F of AS and Y. Okay, so that's that. Now the second term is RS. So RS is just the empirical error. It is the error evaluated using your training examples. And also when you evaluate it, you don't have a weight associated with it. It's a uniform evaluation. Each example is the same weight. So F of AS is again just the output of the neural network. Okay. So a primary challenge of analyzing the generalization gap really is from the dependence of the F sub AS on the same data set S used in the definition of the empirical error RS. This is really the key of why, generalization, the challenge of characterizing generalization gap. And that's why, we've always tried to use this kind of complexity theory to somehow characterize the generalization gap, right? So we've used union bound and stuff like that. But here, what people usually do is that they were just doing this kind of relaxation here. So you can see the first, can you see my cursor, guys?
Yes.
Okay, wonderful. So, we were just saying the generalization gap is upper bounded by this term minus this RS of F. So now RS of F is, you're not very surprising, this is just corresponding to that. But more important, I'm just replacing F of AS with any F within my hypothesis class F. Okay, so before we were using just use small h, in capital H, but this capital F here is just the hypothesis class, and this is just one hypothesis, right? So you're just taking the supermode of that because that would definitely be an upper bound. So you can just get around with this dependence on the same, the dependence of the FAS on the same data set as used in the definition of RS. Okay, that's how you get around with that problem. So any questions? Sorry, I don't know why my slides are not rendering correctly. Somehow later parts you can ignore all these, but look at this, okay? Okay, so now, several approaches in statistical learning theory are trying to do the following. First is the hypothesis space complexity. Okay, so what they are saying is that here, essentially, we're focusing here. So with high probability, so this is very similar to what we see in our generalization bounds in our previous lectures, right? So with high probability, this gap, this upper bound, which is bounding this generalization gap. So this gap, upper bound of this gap is gonna be upper bounded by the complexity of the hypothesis class L of F. It's just the complexity of the hypothesis class. Summation of the square root logarithm 1 over delta over m or 2m. All right, so we're very familiar with this term, right? So essentially, what does this mean? This is basically, it's a bound on the complexity of the hypothesis space, right? So unfortunately, this complexity of hypothesis space, there are two lines of researchers trying to characterize this complexity of hypothesis space, right? This is RM of LF. Unfortunately, one line of work show that is exponential dependence on the depth. So what does this mean? This means that deep neural networks have to overfit, which is not, which is again, inconsistent with our understanding. But somehow I wanted to later argue that this is not an inconsistency, but right now we're thinking this is an inconsistency, okay? Since we haven't talked about that yet. Now this is that. Now the second line of work trying to get in bounds on this hypothesis-based complexity is this, they have linear dependence on the number of parameters. And this is also bad news because number of parameters is just very large, right? Very, very large. Essentially, if you are to look at something like this, then you can get only vacuous bounds. These complexities have to be very, very large for any of these bounds to make any sense or have any meaning in terms of guiding the generalization gap. Because we know that generalization gap has to be upper bounded by 1. If these things are greater than 1, then we don't have, doesn't make any sense. Okay. Usually, the thing is these number of parameters are usually much higher than the number of examples, right, in neural network domains. So therefore, many of these bounds are just not, they're going to be large. Let's put it that way. Okay. So this is one line of work in statistical learning theory, it's a hypothesis-based complexity. Now the second line of work is this so-called stability approach. So what is the stability approach? Which is trying to deal with the dependence of the F sub AS on the data set S by considering the stability of algorithm with respect to different data sets. So that seems to be a little bit strange. Let me say that again. So it's the deal with the dependence of F sub AS on the data set S by considering the stability of algorithm with respect to different data sets. Okay, so it is, there's the so-called stability measure. What it does is kind of a measure of how much changing a data point in S can change the final output of the neural network. So if algorithm A has uniform stability with respect to L, and if the codomain of the L is in 0, M, then with high probability, with high probability, you get this result. Of course, we don't know how to prove this, but this is something that people have already seen. And essentially, what this means is that you can come up with an upper bound in terms of the stability of the stability of instead of having like a hypothesis-based complexity measure, you have a stability measure, and this stability measure you can see the upper bound becomes something dependent on the beta, right? Beta here and also have beta here. Okay, so based on the previous work on stability, one may conjecture some reasoning for generalization in deep learning as long as you can give a very small stability of the algorithms. That's another line of research. However, I don't think people have been very successfully coming up with like a stability, a stability that gives you also very good accuracy. A small stability, sorry, that also gives you very, very good accuracy. So So other than the stability, there is the third line of work, which is the robustness. So this is different from, what you guys, many of you are familiar with, the robustness of neural network in terms of adversarial correlations. So this is different. So the robustness is essentially avoid dealing with certain details of the dependence of FAS on S by considering the robustness of the algorithm for all possible data sets. So that's the idea of robustness, and it is a measure of how much the loss value varies with respect to the input space of the XY. Okay, so people have also come up with the omega psi robustness. Essentially, what that is I don't know what's going on. So let me look at let's look at this. Sorry, my slides are not rendering correctly. So, again, this is like an upper bound in terms of this generalization gap. And it turns out this upper bound is related to psi of S summation of M square root of these terms here. So the robustness approach requires somehow a priori, like the partition, a fixed partition of the input space, such that the number of stats in a partition is omega. So this is rather difficult, actually. And the change of the loss value in each set of the partition is bounded by psi of S for all S. So that, so somehow, although this seems to be a simple assumption, but in practice is really hard to realize. So that's why, we don't, again, the statistical learning theory in terms of robustness is not necessarily a very successful way of describing or understanding generalization. Now, this paper talks about the fourth direction, which is the flat minimum. I know that after this work, there have been other works of like better definition of what's a flat minima, what's a sharp minima. But when this paper was out, they're claiming that the flat minima also not necessarily is a very useful tool for understanding generalization, only because the flat minima is like it's just a small perturbation in the parameter space around a solution that results in a small change in the loss surface, and that's how they define a flat minima. And basically flat minima can be viewed as like a concept of low variation in the parameter space. And people have been using flat minima to understand generalization. However, this paper, Ding et al. In 2017 showed that the flat minima in practice deep learning hypothesis space can be turned into sharp minima through some reparameterization without affecting the generalization gap. So therefore, under the same generalization gap, you can just transform a flat minima into a sharp minima. Therefore, we still need to understand better about the flat minima or the sharp minima in terms of understanding generalization. Okay, but later on, there are some follow-up works on understanding flat minima and sharp minima, and I do think some of them are pretty interesting. So, I just don't want it to mislead everyone into thinking that flat minima and sharp minima are not useful at all in terms of understanding generalization. Okay, so most importantly, in the last 5 minutes, I wanted to emphasize, what I think the most important thing in this paper is actually people are saying in the previous paper, Zhang et al., right? So the previous paper of rethinking generalization, the empirical observations in that paper seems to contradict with statistical learning theory. And that's what the authors are kind of saying, right? Although kind of implicit. So is that really true? Right. So what's really interesting is that I think this, the authors of this paper provide a very, very good understanding of this so-called inconsistency. So these inconsistencies are really not inconsistencies. They are simply from misunderstanding or misuse of this learning theory. First of all, the most important thing here is that we have to understand this very well because we just learned about this statistical learning theory. First,
people, it's true to say, oh, what's going on? So it's correct to say that the hypothesis space complexity small implies that the generalization gap is small. Why? So I'm saying that this is true. Why? Any thinking why?
That's the direction we proved.
Yeah, sure. But yeah, do you want to give like more intuitions why that's the direction we proved? Think about the upper bound, So we're saying that the generalization gap is upper bounded by the hypothesis complexity, like some function of hypothesis complexity. Do you agree? That's all the statistical learning theory has been saying, right? So what does this mean? This means that if the upper bound is small, then the generalization gap has to be small, right? So that's why it means that the hypothesis space complexity small implies the generalization gap is small. Okay, so that's a valid direction. However, many people misunderstand this as in, if the generalization gap is small, that means the hypothesis space complexity is also small, but that's not necessarily true. Why? You have some quantity that is small, that does not mean that an upper bound of that quantity is small, right? That's a very simple logic kind of, loophole here, right? So something is small doesn't mean that the upper bound of that thing is small. So that's why a lot of misunderstanding is coming from this, right? So from the previous paper, we see this generalization gap is small from empirical observations. Now we see, oh, but from theory, the hypothesis complexity is just high. So that's contradicting. That's not, because small generalization gap does not mean the hypothesis space complexity is small. That's very important to understand. So that's the first misunderstanding. However, that being said, I still think that we need to find a good upper bound. So the upper bound that is also small when the generalization gap is small. Do you agree? So that means these bounds are not very good indications or not very useful in terms of understanding deep neural nets. And that's why at the beginning of that paper, the second bullet point of the conclusion, I said, I agree with that argument. I think we're yet, to find a good measure to measure the complexity of these models. We still don't have a good measure to measure the complexity. Okay, so that's very important. That's the first misunderstanding. Then the second misunderstanding is a little bit more trivial. Oh, first of all, any questions regarding the first misunderstanding?
I just wanted to ask, so you're saying maybe if we find sort of a correct characterization here for the complexity of a hypothesis space, we can get this implication to go both ways?
Not both ways. Yeah, again, oh, sorry. Okay, so maybe we can leave the second arguments next time. Sorry, I don't want it to, again, take everyone's time. But that's not, again, this direction is just simply not true. The reason is that, something is small cannot imply that the upper bound is small. But I'm hoping that the upper bound is very close to that small, to that something that we're trying to characterize. Do you see?
Yes.
Yeah, but I think your understanding is correct, but it's just that I wanted to make sure that this, the mathematical logic thinking of this is very crystal clear. Okay. All right, so, I want to stop here. I don't want to take everyone's time, but, we will start with this slide next time. Okay. See you, everyone. And we do have office hours now.